Let's analyze what happens if a particle is trying to move in the inside surface of a rough funnel in a horizontal circle. Now, before this discussion, let's once again review the case of this smooth funnel. See, when you have a smooth funnel and a particle is moving in a horizontal circle with speed v, the speed should be root of gh. So exactly for that speed, the particle will nicely move in the horizontal circle over there. If the particle is projected at a particular height with a speed more than root of gh, then what will happen is this particle will kind of spiral out to a greater height, and once it reaches the height where that speed with which you are projected, if that matches with root of gh, it will go to that height and it will move in a circle. Whereas if you project it at a speed lesser than root of gh, it will spiral in to the funnel, and once it reaches a height which where v matches with root of g into that height, at that height it will start moving in the circle for the case of smooth funnel. So at a particular height there can be exactly only one speed with which the particle can go in a horizontal circle. But now when we analyze the case of rough funnel, look at this. Now if suppose a speed is low, then there is a possibility for this particle to move a spiral into the funnel. Like that it will try to spiral in, but then now there is friction. So now friction will try to oppose that, and friction will always act along the tangent direction to the rough surface. So friction is acting along the tangent of that funnel line. See, funnel line is going to be the tangent. This is the tangent line. Perpendicular to that is the normal line. So this is tangent and normal. So friction acts along tangent. Since I'm taking, if speed is low, the particle has a tendency to spiral in, friction will be acting in that direction. And now I'm marking the angle of the funnel to be alpha like this. I'm not taking the angle made by slant height with the vertical, because we are going to kind of extend the same discussion to that of inclined plane banking of roads. Exactly same ideas only. So let me now consider this angle to be alpha, the angle of inclination of the slant height with the horizontal. Now if you make the FBD, the mg, normal contact force, and friction, which will be static in nature, tries to prevent that particle from sliding inwards when that speed is low. Now if you resolve the forces, note that along the center or towards the center point, here you have n sine alpha, and I'm assuming that this friction has just become limiting in nature for a particular value of speed. So I'm writing this friction force equal to mu times n, and mu n cos alpha will be equal to the horizontal component. So net force towards the center radial line n sine alpha minus mu n cos alpha will be equal to mv square by r. Likewise, in the vertical direction, net force must balance. So we can say n cos alpha vertical component and mu n sine alpha vertical component. That should balance the weight of the object. You solve the two equations. Basically, you divide so that n will get cancelled out. So you will get one relation for v square, from which you can get v value. Now that v value which we get, that is the minimum speed with which the particle could be moving in a circle for a particular radius of the circle. So note r is radius. For a particular radius, the minimum speed with which the particle can move will be this expression. Now obviously you note that this expression makes sense only when tan alpha is greater than mu. Why? Because if tan alpha is lesser than mu, just recollect inclined plane discussion. So if you have an inclined plane of angle alpha, and if you have one object placed on that particular funnel, if placed on that inclined surface, if tan alpha is lesser than mu, and if you simply leave that object over there, it will not have a tendency to slide down, and it will not be pulled into the funnel in this case. So it will be pulled into the funnel only when tan alpha is going to be greater than mu. So we are assuming that let tan alpha be greater than mu. If tan alpha is greater than mu, and if you simply place an object, means it will slide down into the funnel. So to prevent that, you need to project it with some minimum velocity so that it can continue moving in that horizontal circle, and that minimum velocity is this expression. Likewise, we can even get the expression for the maximum velocity. The only change is, if you're going to give a high speed, then the tendency of this object would be to spiral out and gain height inside the funnel. So now the friction force will be trying to prevent that by acting towards the vertex point as shown in the diagram, and other forces, mg normal force, they are going to be there. Now the net radial force, that will be n sin alpha plus mu n cos alpha, that should be equal to mv square by r. And similarly, you take a vertical component, n cos alpha minus mu and sin alpha should be mg. You divide the two equations, you will get this relation. And V max, that will be equal to root of Rg into tan alpha plus mu by 1 minus mu tan alpha. So this is the maximum speed for a given radius along the inner side of the funnel. So if you project it with more than this speed, then the particle will spiral out. And if you project it with lesser than this particular speed, then the particle will spiral in for a rough funnel. That's the discussion. In fact, you can try to, if you can remember these expressions, you can remember, but you should also clearly understand that you will make FBD. The only point you have to note is when you make FBD for high speed, show friction down and take the net force along radial line, write the equation. Along the vertical direction, net force, you balance it and get the required expressions. You divide the two equations, you will get it. So if you remember the procedure behind how to make FBD and solve, it is better for both the cases. Just that friction direction, you have to be careful while you are analyzing for minimum speed and maximum speed. Right, so that's about this particular discussion. The exact same ideas can be used for banking of roads as well. Exactly same conditions. Just that the slant height of the funnel would become the inclined plane. That's all.